Dr. Manish Sharma obtained his B.Tech in Electrical Engineering from IIT Kharagpur in 1991 and worked in the integrated circuit industry for 3 years before joining graduate studies at Stanford University in 1994. He obtained MS and PhD degree in Electrical Engineering in 96, PhD in 2000. During 2000 to 2006, he was a research scientist at Hewlett-Packard Research Laboratories in Palo Alto, California, working on materials for magnetic random access memory applications, nanolithography, and on the MEMS-based biological sensors. Since 2006, he has been at IIT Delhi, first with Department of Physics and now at Center for Applied Research in Electronics, where he is currently an associate professor. And let me add that he is also coordinating and the principal coordinator of a giant project on nanofabrication, which is under which a nanofabrication facility is being created in IIT Delhi, and Dr. Manish Sharma is the principal coordinator of this facility. So I invite Dr. Sharma to give his invited lectures on magnetic nanostructures at RF frequencies and computing applications.
I'll be discussing magnetic materials and devices made with magnetic materials. However, this is a computing and quantum computing symposium, so I will actually discuss the last part showing how magnetic materials can actually be used to make devices for new computing applications. So I'll try to link one part of my work, which is basic material science, with the devices part, and I'll start with a brief history of magnetic materials and how they have been used traditionally in computing. One of the most important things that they have been used throughout for computers is for storage devices. So I'll just give you a very quick history of how they are used for storing memory, and then I'll go to the rest of the part of this talk. Very briefly, most of the work that I do is related to magnetic materials, but the kind of applications that I work on are jointly with several faculty. The principal work that I do is work on nanomaterials, nanowires and nanoparticles for testing their magnetic properties at gigahertz frequencies. So there is a very practical application for this. This is for high frequency inductors for application in a cell phone. That is part of the work that I do. Another work is pattern media for storage, and that is more basic materials work. I also work with other faculty in the physics and the biochemical engineering departments. With the physics people, I am working on graphene. My work is largely the experimental part, but the PhD students I share with people in physics, they work on the theoretical modeling of the electron transport, especially in the presence of magnetic fields in graphene. The other work I also do with the biochemical engineering department, we won't be talking about this part today, is related to the synthesis of nanomagnets using bacteria. These are natural bacteria which synthesize nanomagnets. So I am mostly interested in the materials characterization of those magnetic materials. So I'll start with a very, very fast review of how magnetic devices have been traditionally used in computing. One of the first storage mechanisms has been iron, it's actually iron oxide. It's actually an iron wire which is wound around like a rheostat on a spiral coil, and the top surface of the iron gets oxidized, so it becomes iron oxide. And what you are doing is, by applying very high fields from an inductive coiled head, you can magnetize or demagnetize parts of the wire. So this is a very, very early form of storage. It was first demonstrated, I believe, in 1910 or 1908 as a practical device. So it's actually the way magnetized, it's actually a piano wire on a cylinder, and it was in fact really quite reliable. So you could store data on it for several years. Of course, the storage density was very low, but you really could store serial data along the wire over a long period. So obviously I'll skip quite a few stages in between because this is going to be otherwise a very long talk. But one of the common devices which we were aware of at least till 5-10 years ago, let's say 10 years ago, was the cassette tape. It's still used a lot, especially by people who deal with high fidelity audio recording, and that's basically the cassette tape. A different version of it was obviously used for videotapes, where the recording mechanism, the material is the same, but the mechanism by which you record is different, because it goes, instead of bit by bit storage along the cassette, along the tape, it's actually what is called helical recording. So the bits are actually in a helical pattern on the same tape. It gives certain advantages in terms of reliability. So, but the point is that these devices are all serial storage and sort of serial access. So if you want to read or write, you have to know where you are in a serial data. Then you go to a hard disk drive, which fortunately or unfortunately is still being used, although it's one of the very old media. The good thing about a hard disk drive is it is semi-random access. You can actually move the head back and forth and access somewhere along the platter where the data is stored. However, it's not truly random access. You still have to, once you go and latch onto a track, you still have to go serially along that track to read or write data. So you could call it not necessarily 1D, but not necessarily totally random access as well. So some people call it 1.5D random access. So it's between the first and the second dimensions of storage. One of the reasons why the hard disk drive has been so successful, the first commercial available ones were made by IBM. It was called RAMAC, so Random Access Memory for Computer Storage, some acronym like that. It was available in 52 or 54. I was trying to get a decent picture of it, but I couldn't find one, so I haven't put it here. But since then, even today, the best way to store computer data, especially large amounts, has been the magnetic hard disk drive. And nowadays you can buy terabytes of data for less than $100. And I'll come back to what the storage density means here. So there are actually different ways of storing data. One is what is called longitudinal, another is called perpendicular recording. The reason I'm showing this slide is essentially what is happening is, as you store data longitudinally, the bits have very high demagnetizing field and they don't like to point head on, and it is better to have them aligned perpendicular to the plane of the medium. So perpendicular recording allows you to go to much higher storage densities and also slightly faster read-write access. However, it has its own problems in terms of how the head and how the media is designed. This is what is called CPP, current perpendicular to plane kind of geometry for the read access, and then the perpendicular medium itself has to be slowly, as the densities go up, the medium also has to be improved further, which brings me to the real point of this. So everybody here is probably familiar with the Moore's law, but the Moore's law is not valid just for CMOS chips, doubling every 18 months or doubling every 2 years. It's actually valid for a series of components, pretty much all components related to computers. And this is a curve which is from Hitachi's website, and Hitachi really boasts it, or IBM rather. They boast that hard disk drives have always been following the Moore's law at an accelerated pace compared to CMOS chips. So they actually double close to, depending on where you are along this curve, the areal densities, gigabits per square inch of storage, doubles every 9 to 10 months. Recently it's a little slower, but I've marked the last announcement from 2009, which is we are already reaching 1,000 gigabits per square inch, right? Yes. So that typically people think is pretty much the limit of hard disk drives in terms of storage data. There is a big penalty when you store a gigabit of information in a square inch. Yes, you can make the hard disk drive smaller. However, you have to spin it faster in order to access it, and that has its own power requirements. So essentially people think that maybe another 5-10 years you'll start going to flash as the main storage. However, that's what people thought 10 years ago. The biggest thing here is that the way the technology has advanced is different from the way CMOS chips have advanced. So the Moore's law works for CMOS chips because of lithography. So people have been able to scale down further and further the basic component of all CMOS, which is the FET, because you can scale the gate length, you can scale the contacts, the whole lithography shrinks the size of the gate, whereas the functionality of the gate remains the same. However, in the case of the hard disk drive, the advances which make the Moore's law possible are different. They are essentially not about scaling by lithography. They are about scaling the read and the write head, and they are about scaling the patterned media. So this picture is essentially about how the hard disk drive medium will scale further. When you go above 250 gigabits per square inch, you can't use continuous media for either perpendicular or parallel kind of storage. You have to go to patterned media. So each of this is a nanomagnet, which is essentially a pillar of cobalt chrome, and it's about, the dimensions here are not clear, but this distance is about 50 nanometers, and the height of these pillars is about 150 nanometers. So those are the kind of dimensions where you go down to single domain physics for the switching of the media. So we've gone from tapes to disk drives and finally to RAM, or rather truly addressable random access memory. So CMOS, when you have SDRAM, like static or dynamic RAM, you can address it using row and column independently. So that's one good thing. Magnetic materials have also been used for storing information in a truly random way. This is one of the first examples of a core memory from 1950s. What you see on this picture is actually the zoomed in version. Each and every core here is a ferrite core which stores 1 bit of information. However, what is more interesting is that it's actually woven into a fabric. So all these fabric that you see here are interconnects which are for winding up the core together to form one single big block of memory. And what you see here is a $10,000 cube, and the total capacity of this is 52 kilobits in an 8 by 8 by 8 inch cube. So it's a random access memory from the 50s. The good thing about it is it actually works really very fast compared to SRAMs and DRAMs. It is limited not by the switching speed of inherent or in the magnetic bit, it is actually limited by the current drivers which could drive the fabric. So I'll come back to that point in the later part of my talk. So the same kind of MRAM was, sorry, the black isn't coming very well. This is a different version of MRAM, which was, this is from 1986. This was made by Honeywell. and it consists of a 256 kilobit chip, and essentially it uses an isotropic magnetoresistance, AMR effect, as the storage mechanism. The only way they could advance it further was going to new physics. So this is the difference between CMOS versus magnetic technology. CMOS, the new physics hasn't come in, hasn't kicked in terms of scaling the FET. The new physics in the case of MRAM or in case of hard disk drives has always had to kick in to go into the next level of technology. So nowadays they use what is called spin dependent tunneling based MRAM. This essentially uses a ferromagnet insulator, ferromagnet tunnel junction to store the bit, and using that, I'll give you some examples. So this is from where I used to work. This is a 3-conductor MRAM. We demonstrated 1 gigabit MRAM in 2003. So what you see here is a single layer of MRAM, and it's actually designed to be sandwiched between the copper damascene layers at the interconnect level. So this is planarized copper interconnect layer 1, and this is copper 2, and this thin black line is where the magnetic tunnel junction layer is stored. So it's planarized and made in such a way that if you wanted to make multiple layers, you could actually potentially stack it. So this demonstration chip was done on a 6-inch wafer, and each chip is 1 gigabit, including all the working CMOS with this. However, this was designed to be high density, low speed. The other versions of this come from IBM and Motorola, and these are from 2004 and then 2009. So Motorola actually used to make this, then eventually it got separated into a separate company. It's a spin-off, the company is called Everspin, and they make an MRAM where you can get 256 megabit chips, and we won't be talking about the other parts of the MRAM, but actually we will go on to see how the toggle mode switching part of the MRAM works. So the new physics here which allowed them to go to such higher densities is essentially what is called a toggle mode switching MRAM, which consists of a pillar of anti-parallel layers, and what you are doing is you are applying a series of fields, usually 2 or more fields, in a sequence with a certain phase. So when you apply the first layer and then you apply the second layer, what happens is you cause the storage layer to start swinging around and precessing in its motion, in its moment, and then that precessional motion causes the MRAM to kick to the other side. If you don't apply the second field, it will spiral back and settle to the original bit. However, instead of that, if you apply the second field, that is sufficient to kick it into another phase diagram of its switching curve, which stabilizes it and then switches it and locks it in the other part of the curve. Potentially you could use it for multi-level logic, but that gets into noise thresholds which are not very good. So usually they design only 2-bit logic with this, 2-bit storage with this. But more importantly, if you actually work out how fast this switches along the precessional motion from one side to the other side, it switches at sub-nanosecond regimes. So that's the basic importance of this kind of switching mechanism. It allows you to go really very fast. So you will be limited not by the inherent physics of the switching mechanism as you are if you use charge-based storage in the case of DRAM cells or SRAM cells. Here you will be mainly limited by the current drivers and other things. So the basic physics of how the storage is there, and if you want to write or read it, it doesn't limit you. So we'll come back to these few points in the third part of the talk when I start using them for making computing devices. But the point that I have to make here is that most of the magnetic devices have been used mostly for storage. not for making a processing device or a computer in the sense of a switch, like the way a FET exists. The other thing is, you do switch bits from logic 1 to logic 0 or otherwise. However, all that is done using static switching. You don't use dynamic switching. If you really go into toggle mode dynamic switching, you actually can go to sub-nanosecond time scales. So, if we really manage to do that properly, you would inherently have a very fast memory and a very fast processor. So, those are some things which I will describe in the later part of the talk. So, we will go on to the second part where I will describe some of the devices that we do make in our lab. These are related to how magnetic materials work at RF frequencies. So, some of the devices that I am looking at now are related to these pattern media storage materials, and these are essentially pillars of magnetic materials which are typically cobalt chrome platinum when I use hard magnetic materials, or nickel oxide for antiferromagnetic or cobalt materials. So, we try to make nanowires arranged in regular arrays. The regular arrays are usually done by lithography or essentially nanoimprint lithography or E-beam, and the irregular or densely packed arrays are done using alumina templates, using electrodeposition. The point is that most of these wires that you see here are one-dimensional. You are restricted in the XY plane, but the Z axis, the height of the wire, is variable. And if you use more than one material during the deposition, if you make a multi-layered nanowire, then you get what is called a magnonic crystal. So, essentially it is a periodic array of magnetic materials in both the XY plane as well as, if you decide to make a multi-layer, in the Z axis as well. There are several things. It is not that easy to make these materials because they tend to intermix. You have to have very sharp boundaries, especially if you are going to mix, you layer magnetic versus non-magnetic materials, or you put a metal and then an oxide, etc. That is not easy. Today we will just talk about electrodeposition using nanowires for cobalt and cobalt chrome materials. Sorry, the black is not very good here. Anyway, so we essentially work with a specially designed electrochemical deposition cell which allows us to deposit sub-monolayer materials one at a time, and it has a membrane where we apply a potential which allows us to segregate two different metal ions. So, that allows us to modulate the rate at which layer 1 and layer 2 will get deposited. These are the kind of templates we use, and these are the kind of nanowires we grow. These are cobalt palladium nanowires with really sharp interfaces. So, if you zoom in here, you can actually see the palladium, which is the dark area starting from about here till about here, and then the interface is extremely sharp. What that means is the cobalt and the palladium, the magnetic and the non-magnetic interface is extremely sharp, and it will not scatter spins. Rather, if you have a diffuse interface, you get what is called spin flip scattering at the interface, and that destroys the magnetic transport in such nanowires. So, this one is actually a picture of similar nanowires, except it has not come out very well, but what you see is actually, these are actually not nanowires, these are hollow nanotubes. So, we have actually made cobalt nanotubes using this deposition technique, which are 100 nanometers in diameter, outer diameter, and 50 to 70 nanometers of the inner core of these is hollow. And in the case of cobalt palladium multilayers, we get what is like a bamboo structure. So you would have nodes of palladium and then hollow tubes of cobalt stacked on top of each other. What does that mean? That actually means that you can make a magnetic crystal in 3 dimensions and then launch spin waves, which is something we will discuss just in a little while, launch spin waves along the nanowires and study how the length of each segment can change. So magnetic crystals, very briefly in a crude fashion, are the microwave analogs of photonic crystals. So photonic crystals are periodic structures which give you band structure and other metamaterial effects at optical frequencies. If you use magnetic materials, you can engineer them and see similar effects at gigahertz frequencies. So sort of from 500 megahertz up to about 40 gigahertz. But you have to learn how to deal with microwaves, which is not easy. So the kind of devices that we make, we connect them to spectrum analyzers. You have to make a RF cage to isolate them. These are the kind of devices that we make. This is a jig which allows us to position the sample right here. What you see here is a copper bow tie antenna to concentrate the field. The field is generated by a RF transmission line which is buried under this substrate, and there is a separate bias line for the bow tie. What it does is it essentially launches a pulse of magnetic, essentially an electromagnetic field pulse along the transmission line. When it comes close to the bow tie acts as a near field antenna, focuses the wave and causes a very sharp magnetic field to be applied right where you put the sample. So if you do that and then you sweep the frequency, what you get is an absorption curve over a certain band. Sorry, I used black again here. So this is essentially from 8 to 20 gigahertz, this scale, and what you can do is you can measure the return loss at different frequencies of any wave that you launch in the transmission line. And essentially if you apply an external field, a DC bias field, you can shift the return loss where you get the maximum return loss. So this is in terms of frequency. I'll show you the time domain curves for this as well later. But what it tells you is that certain frequencies, this is acting as a tunable filter. So at certain frequencies it will absorb the wave which is going through the transmission line. At other frequencies it's just going to let it go through. So you can do the same thing using ESR or FMR spectrometers as well. You would essentially get a very sharp modulated peak of absorption. Typically you get a very broad absorption which corresponds to sort of electron spin resonances at the atomic level from the electron sort of cloud which exists in your metal. But when you get a very narrow peak like this in the frequency domain, what essentially it means is you have an FMR absorption, not an ESR absorption. So this is the kind of structure that we make, and just to show you, this sort of propagation can be modeled directly using micromagnetic modeling, and what you are seeing on the right are the FMR modes of the material that we made, the array of nanowires, and it shifts as a function of applied voltages and essentially applied fields. And the same thing, if you have a Fourier transform, you can actually see it in time domain. So what you are seeing is the precessional motion in the 3 directions of the spins of each of the nanowires together, and each of these curves is essentially telling you the way the nanowire is launching a spin wave from one side to the other. And as a function of the applied field, you can tune which particular mode gets excited. So we've actually tried to make a tunable filter with this. We've got some results, not particularly great because better results have been published by others. You can use this material to make negative refractive index materials as well. This is some results which were published way back in 2001. So if you are a material scientist and if you don't read electronics literature, this is what happens. So I started working on this problem, and then I realized that the microwave people knew about metamaterials in a different sense of the term, and they've been doing similar things, however at very different geometries. So they made some devices which are called circulators. You have multiple ports and you can launch the signal in one end and get it on the other side. Okay. So now I'll come to the third part of my talk, which is how to use these magnetic devices, especially this precessional switching and storage in magnetic devices, and make some real applied computing device with this. So before that, I'm just going to show a couple of slides that these are other slightly different branches of magnetic applications of materials, such as essentially people have tried to use the spin degree of freedom of electrons for quite a while. So pretty much all CMOS works on only manipulating the charge, so essentially the mobility of devices. However, there have been proposals that you could somehow have majority spin and minority spin electrons somehow segregated in the same semiconductor and then manipulate how they transfer. So I'll just mention a couple of major issues in terms of materials which have been there with magnetic, this kind of separation of spins. The first problem is you can't inject polarized electrons, spin polarized electrons into a material that efficiently. So people have been working with gallium manganese arsenide and gallium arsenide mainly because it is one of the best materials with the longest, what is called the spin, the relaxation length. So essentially, when you inject polarized electrons in any semiconductor, there is no preference for one versus the other spin channel. The spin up and the spin down channels, there is a major amount of scattering between the two. The probability of scattering electrons from spin up to spin down or vice versa is very high. So in the case of gallium arsenide, the relaxation lengths, the spin relaxation lengths are very long. Very long in the sense that all you want is several hundred microns. You don't want more. People have proposed using a 2D electron gas to manipulate this, and there have been different geometries for this. Most of the work on gallium manganese arsenide was done much earlier. People still do it. And the other issue actually which I haven't mentioned here is related to what is called spin injection. So transferring, if you have a ferromagnet metal, it has at the Fermi level spin up or spin down, whichever way you want to think about it. You have a major difference of the density of states of one versus the other electron. However, to transfer that into the semiconductor, the interface has to be engineered. It's only recently in 2009, 2010 that people have started publishing results where they managed to get efficient spin injection into the semiconductor. So today I'll discuss some of the work that we are trying to do using precessional transport of signal through transmission lines. We try to launch the spin wave in a ferromagnetic film. So you actually have a very thin ferromagnetic film, and it is separated from a transmission line structure atop by an insulating layer. And what essentially happens is, if you have a ferromagnetic film and you apply a very high tuned field, a pulse on one side, it launches a spin wave which causes precessional switching along the ferromagnetic film. What we will eventually do is replace this film with a layer of nanowires. But today I'll just show you some basic results on how switching happens in such a very thin layer of ferromagnet. So we usually pattern what are called asymmetric coplanar waveguides atop the ferromagnetic film. There are some other geometries where we apply the same thing below the ferromagnetic film as well. And what you are doing is, as the spin wave is processing from this point to another point, you are launching what we'll call a logic signal from one end of the chip to the other. So at any time, the logic signal here versus this logic signal here would have a phase lag. So you have to always remember the phase lag, but that is directly related to the distance, the way you make the transmission lines. So if you apply the correct phase signal, if you launch a wave here, you can reach the other side and receive it with the right phase. You just have to apply a small delta phi depending on the distance traveled. The same thing can actually be used for making a switch or a FET, where essentially what you're doing is you're applying a pulse on one side and the pulse is propagating from a source towards a drain. What you're seeing here are three transistors. So sort of a source drain here and a source drain here and a source drain here. And since the ferromagnet film is where you have a spin wave, if you apply a voltage and you apply a gating current, you can actually apply a voltage here and receive it there and gate it in the middle. So essentially what you get is a FET where you can controllably switch on or off your spin wave. There are some issues with it. You have to start with an injection of electrons. Ideally you want a half metallic injection from sort of the source of the electrons, but that's not absolutely important. But yes, the ferromagnet film has to be quite good so that the spin wave can propagate for long distances. So if you simulate and you can actually model this, depending on the distance that you have between 2 points, you would essentially get this sort of precessional spin wave launched in the device. And we've done some measurements on an array of nanowires in our coplanar waveguide, where the nanowires were actually connected at the bottom. So we are launching the spin wave in one end and then seeing the delay caused by the presence of the nanowires, which acts as a gating circuit. And then as we change the magnetic field, you can apply different amounts of gating voltages. So you can actually plot as a function of, by repeated measurements, by different delays, you can plot the kind of precessional wave which is being launched here. Most of the noise that you see here is related to the phase difference between the input signal and the output signal. There are people who've done logic design using this. What we are trying to demonstrate is only the basic gating mechanism, but people at the computer architecture level have taken this sort of model, and it was originally proposed by a group at UCLA, and this was way back in 2002, 2003, and essentially what they did was they modeled the whole logic that you would build with this computing device. The key point here is it happens really very fast. The other thing that is important, which I don't have time to show maybe, is actually when the signal travels in one direction, as long as most of the time you don't saturate the spins in any particular region. You are only exciting a very small amount of spins. So if you launch a wave in one direction and if you design it in such a way that you have another wave or a line in this direction, the precessional logic signal, if you will, in one direction versus the other will just cross each other. It will just superpose in a small region and then just cross. So you don't need interconnects to route this signal from one end of the chip to the other. So you don't have to go up and then down again through interconnects. So that's like a good benefit of this sort of design. The group, in some of their papers, they've extended the logic to have a multiplexer or a bridge circuit with multiple ports where signals are bouncing from one to the other, and there are some transistors which allow you to switch the signal from one end of the multiplexer to the other. But anyway, we are more interested in demonstrating the basic working of the FET, and I think we've been reasonably successful up till now. So I'll conclude my talk. It is possible to make spin wave based computing devices, but there are some real serious issues. You have to work at RF frequencies, and you have to learn how to do RF design and control of spins independent of the semiconductor part. But the good thing is you are working mostly with metallic systems, especially which have been very well understood by the magnetics industry, and most of the processing is compatible with semiconductor CMOS. So in the future you could take some of these devices and connect it with CMOS circuitry if you wanted on the same wafer. So that sort of merging with CMOS is quite possible. Okay, thank you.